For something a little bit different, I'm going to take a look at Quadsort. Here on the GitHub page, Quadsort is a branchless, stable, adaptive merge sort, faster than Quicksort. Not sure which Quicksort that's faster than. Let's take a peek. Okay, here's the code. It's written in 100% C. I believe it's pretty well optimized too. And let's have a look at what it does. It's a stable, fine, okay, bottom up. So this is a merge sort that's going to do exactly like what TimSort does, where you sort the small patches one by one, then you merge those patches and so on from the bottom up, rather than doing a recursive split down. Okay, that makes sense, save being recursive. Branchless would normally mean there are no comparisons. I guess it's avoiding some comparisons so that the you don't have branch prediction in the CPU. And it's a merge sort named Quadsort. Okay, so things it's got. A Quadsort analyzer, which is what Quadsort begins with. This will be one pass through the array. I approve. And it's going to be looking for ordered data, reversed, and try and not impact the performance on random while it does it. Okay. And when it exits, it's got sorted blocks of 8 elements. So it's doing the first pass of the merge sort. When it does the sorting of 8 elements, it's basically going to be using a sorting network in that it's branchless here. It's doing the fixed operations. Cool. And so here's the merge strategy for, this is the standard for bottom up in that it's doing it as a binary. 8 goes into blocks of 32. Oh, so actually, no, that's quad. So it's merging blocks of, it's merging 4 at a time, 32 into 128 and so on. So it's not just doing 2 at a time. Oh, for each ping pong merge sort. Okay, it's not doing 8. What it's doing is it's doing a merge of 2 and then it's doing another merge of 2. It's just that he's talking about it going from one patch of memory to another to do a merge of 2, and then the merge of those, which will be a 4 in total, comes back to the original piece of memory. So it's a merge sort, but just moving back and forward. That's okay. Cool. Okay, in terms of benchmarking, let's see how quick it is compared to some other sorts. And here we go. So I was reasonably careful. I have compiled it according to specification using O3, so it's trying to optimize. And also, I believe in the source code, there is a note here that we want to uncomment this for faster primitive comparisons. That we're going to do integers, so that makes sense. It's just going to compare the values directly rather than following a pointer. All right, results-wise, Quadsort. I've put it in here with the dashed line. I've removed the TimSort implementation because it was slower than everything. Random data, it's not bad. It's not quicker than Quicksort. It is slower than Quicksort on the random. So this is green being the NumPy C++ implementation. It is quicker than the PDQ sort version of Quicksort. And my current in progress one, I mean, they're the same on the very large, but it's clearly quicker on the smaller input sizes. Okay, next up. This is 11 ascending segments. This should be reasonably good with a merge sort because you've got pre-sorted segments that just have to be merged together. 11 merges and you're finished sorting. And yeah, it's basically the same. That's within a margin of error of the Quicksort simmed. For 20 unique values, this means you're sorting few, like I use modulo 20, so there are only 20 different values, but there can be 1 million of them or 10 million of them, depending on the array size. It is the slowest of everything we've got for the large. It's generally slower than both the PDQ and my current Quicksort, and a lot slower than the simmed one. So that's not a good case for it. We know it does a pass-through at the beginning to find reversed or in order, and so then it does a very quick reverse, and okay, more efficient than what I've written for the smaller arrays, slightly less efficient for the larger. I mean, yes, you do a reverse. How much can you squeeze out of that? And finally, which is probably being masked by my head, so let's do that. For near sorted, which means a lot of it is in order, there's only one swap to make. It is the quickest for small arrays again, and it's slower later. I guess it's detecting the inorderness and skipping them in the same way. That's Quadsort, but on his website, on Git at least, there are a bunch of other sorts as well. This one is crumsort. I tried running several of his other variants of Quadsort, and this was the fastest I could find. This is a hybrid quicksort / merge sort, and he called it crumsort. For no apparent reason. Unstable, adaptive, branchless, has exceptional performance. Well done. It also begins with an analyzer, so it is doing the pass-through to look for fully in order or reverse order using end comparisons. Nice. It also obtains a measure of pre-sortedness for 4 segments of the array, switches to quadsort if a segment is more than 50% ordered. This is why it would be a hybrid. Okay, so if it's largely in order, it will use the merges. So it's trying to get the best of both worlds. For its pivot, it's choosing the pseudo meeting of 9 partitions. Okay, so he's sampling from it. And it does some other stuff. Let's get on to its performance. Right, crumsort's been added in blue. It is also quite efficient for the low ones, but unlike Quadsort, does not get a lot worse for the larger array sizes. It's still maybe 2.5 times slower than the quicksort from NumPy. With the ascending segments, it's probably the same. I mean, it seems to be fractionally slower than Quadsort, but we've just seen it's going to revert to Quadsort. So, of course, same performance. When there are a few values, I suppose quicksort could be good. Still not quite as quick as the NumPy sort, but pretty fast. Reverse sorted. We know it's doing a pass-through. It's actually slightly quicker than the Quadsort. Yeah, I think it's probably real from what I've seen. I was using their own benchmarks, I should also say. So there may be fractionally less overhead here. I think this is comparable. But particularly for lower array sizes, which I couldn't include, I don't think it can be compared to the ones that are in the Golang benchmark harness. Yes, it can reverse quickly. We're probably doing the same kind of reverse. For some near-sorted arrays, again, the same thing. So it's just going to do that detection of sorted segments, and then it's actually going to revert to quadsort again, isn't it? Well, so, upshot, is it exceptionally fast? I mean, it's pretty good implementation. It's quick. It's much better than the quicksort one on the sorts of special cases, right? It's for reversing, it's finding them. It's able to handle near-sorted arrays quite well. So, not bad. I would be pretty happy with that. I'm going to leave it in these charts so we can always compare to them in the future. And maybe I'll get on to another sort later. See you around.